and gentlemen, welcome to the second of the 2013 July Lectures in Physics. For those of you who are new to us, the July Lectures, I'm told, first started in 1968 and have been running continuously ever since. Those of you who were here last week will have enjoyed the lecture by Professor Lloyd Hollenberg on the birth of the quantum atom. The series this year has a coherent theme about the birth of atomic structure and the birth, the nascent ideas of quantum mechanics. Those of you who are regular attendees of the July Lectures will remember a similar coherent series in 2005 celebrating Einstein's theory of relativity, Brownian motion, and the photoelectric effect. We're privileged this evening to welcome the head of the School of Physics of the University of Melbourne. And it's a privilege, above my pay grade actually, to welcome him here this evening. Professor Jameson is a graduate of the University of Melbourne, head of the School of Physics, and this evening will tell us about the connections between the fundamental quantum theory, which was laid down by Bohr 100 years ago in 1913, the trilogy of papers that laid the foundations of quantum theory, and the ensuing 100 years, which have led to the incorporation of the ideas of quantum mechanics into quantum information theory and the possibility of building quantum computers. Ladies and gentlemen, join me in welcoming Professor David Jam.
Well, ladies and gentlemen, good evening. It's a great pleasure to be able to speak to you on this fascinating topic 100 years after the discovery of the quantum atom. I should just mention that last week's speaker, Professor Lloyd Hollenberg, on Thursday afternoon last week went up to Canberra because the Minister for Science, who is, Kim Carr, this week, bestowed on him the Australian Research Council Laureate Fellowship. This is the most distinguished fellowship that it's possible to win from the Australian Research Council. This will bring to Lloyd a program of 5 years of very significant funding to build on some of the things that he told you about last week. So that's a great honour for Lloyd, it's a great honour for the school and for the university. But this week, I don't want to mention diamond. I want to talk mostly about silicon, the most important material of the information technology industry, and show the link back to the discovery of Niels Bohr 100 years ago, the quantum atom. Atoms started a long time ago. As far as we know, Democritus, also famous for discovering a system of government that seems to be better than any of the others, and commemorated on this Greek 100 drachma banknote, which I kept from when I was a backpacker around Greece in 1981. I'm keeping this because it looks like the drachma could come back any day soon. But it does feature Democritus and this now stereotyped, well-recognised symbol for the atom. And indeed, this is the Bohr atom on this 100 drachma banknote. I don't know if Democritus would have imagined it quite like that. But then, after a long hiatus, we fast forward to 1904, when a predecessor in the seat that I'm occupying right now, William Sutherland, published a paper featuring the diffusion relation. This paper described how one set of molecules in a liquid diffuses into another set, and he started by assuming that atoms were real. You have to realise that 100 years ago, or 110 years ago, atoms were thought to be something chemists used as a mathematical convenience to get their equations to come out right. And there was very scant experimental evidence for the atom. So it's remarkable that this diffusion relation came out of these fundamental considerations more than 100 years ago. And this also independently was discovered by Albert Einstein and went into his PhD thesis. He apparently didn't know that Sutherland had already discovered it and published it. This has become Einstein's most highly cited paper. We'll come back to William Sutherland again shortly. But then the man of the moment, Niels Bohr, in 1913, put forward a paper, or three papers actually, in the second half of the year on the quantum atom, which we're now calling the quantum atom. And this was one of the foundational ideas on what we now call the old quantum mechanics. It was remarkable how he managed to get so much from so little evidence. And this quote I really like. It's attributed to Bohr. We don't know if he actually said it or not. It sounds like the sort of thing he'd say. Prediction is very difficult, especially about the future. So then let me fast forward to the other person I want to celebrate tonight, which is Alan Turing. He would be 101 years old this year. He published this paper in 1936 on computable numbers with an application to the Entscheidungsproblem. It's a little bit esoteric, but basically it means how could you ever tell if a computer program ever concludes with an answer? And this was one of the foundational, if not the foundational papers in the physics of information, which previously had been, physics hadn't had much to say about information, and now the physics of information, information theory, and quantum information is a huge field with thousands of workers around the world. So let's just take a break for a moment and look to the future, or rather look to the present from the past. Here are a few things relevant to tonight's lecture. First of all, over here, there was a prediction in 1937 that you could stick a ham sandwich between the poles of a powerful radio transmitter and you could cook it. It seems ludicrous, but of course now everyone has one. This was the birth of the microwave oven. Over here, 1954, the television you'll hang on your wall, and you'll notice it's featuring the Bell X-1, the first supersonic aircraft. There's a modern futuristic thing you might want to look at on your flat television. In 1954, and indeed this has come to pass. Everybody has one of those. Up here, this is fantastic, 1967, this lady is using a newfangled thing called a computer for doing her household budget. And it says in the caption here, this computer is so compact it actually fits into the basement of the house. And one day you might even be able to use it to play games. Now down here, 1959, the prediction that thermonuclear fusion would be able to provide unlimited clean energy for the world. 50 years away then, probably 50 years away today. Over here, 1966, billions of watts of electricity transmitted through the air rather than having to use batteries or plugging your stuff into the power point. And indeed, I was giving a talk at a defence science symposium a year ago, and the batteries in my presenter went flat. And I had to ask around the audience, does anyone have a AAA battery I could use so I could continue my talk? Nobody had one. And I couldn't just pull the power down out of the ether. So looking around here, these three came true, these two are still very far away. But the one down here in the middle came out of Richard Feynman's talk, There's Plenty of Room at the Bottom, a fantastic talk from 1959 where he predicted that one day we would compute with atoms. What he meant there was that we would use quantum mechanics as manifested at the atomic level to encode, process and transmit information. And I would put it to you, ladies and gentlemen, well, you draw the conclusions at the end of today's talk, but this day is drawing very close. So let me just say what a computer is and what we do with them. And harking back to Alan Turing's hypothesis that all computers are basically equivalent to what he called a universal Turing machine. Doesn't matter what the architecture is, whether it uses valves or transistors or integrated circuits or charged ions suspended above electrodes. The basic idea is that you could encode information on a very long tape, you could run the tape through a reader, and the computer could change the value of a binary piece of information, a bit, stored on the tape. It could either leave it the same, you could flip it to the other bit from a 0 to a 1. And this tape runs backwards and forwards through the computer, running an algorithm that's stored in the machine here as it reads and flips the bits depending on the past history in order to solve a problem. But this is a classical computer. Each bit on this tape is either 0 or 1. A quantum computer that I want to talk about tonight will break this equivalence, that we will not have a universal Turing machine because this is based only on classical physics. We'll fast forward to a few years hence, where now our tape will contain the wave function, a quantum mechanical entity which is 0 and 1 simultaneously. And if you Google up unsolved problems in physics, one of the big unsolved problems in physics is whether a universal quantum computer, analogous to Turing's universal Turing machine, has sufficient computer power to efficiently simulate any arbitrary physical system. And by any arbitrary physical system, David Deutsch, who put this question forward as one of the great unsolved physics problems of the 21st century, he means anything in the real world, because the rules of the real world are fundamentally quantum mechanical, not classical, and hence you need qubits, quantum bits, in order to model the real world at the fundamental level. So we'll return to this at the very end there, the qubits streaming through the computer. Now in this talk, I'm going to talk about things that are very small, and so it's important to get a feel for the scale of the nano world, which we're going to have a lot to say about as the talk proceeds. And I cast around, for a good analogy of the nano scale, and Paul Mulvaney did this a lot better at the Royal Society of Victoria a few months ago, but I forgot exactly what the analogy was, so I had to work out a new one. So a nanometer, and most of the things we're going to talk about tonight are 1 nanometer or so in size. 1 nanometer is a billion for the metre, there's a metre. And a nanometer is to that metre ruler as this 10-cent coin is to the planet you're sitting on. Okay? If this was 1 nanometer, the planet would be a metre in diameter. So we're talking about things that are very, very tiny indeed. By the way, if you've got any other spare 10-cent coins, let me have them after the lecture. Even of a funding crisis at the moment. Post-Gonski. But anyway, so when you think nanometer, think 10-cent coin in relation to the planet, roughly. Now, let me start by talking about Niels Bohr and his world. He was strongly influenced by two of the greatest physicists of the early 20th century, Ernest Rutherford and Joseph Thomson. And it's certainly true that in front of every great woman, there is a great man. And here is Niels and his wife, Margarita, on a motorbike, and so much of his early papers that where rough drafts were created and submitted to journals and publications, or speeches that he gave are written in her handwriting. It's clear she had a very, very significant role in his thinking 100 years ago. But the paper we want to celebrate tonight is the one that he published in July in the Philosophical Magazine, published in English, which is a little unusual. The idea of publishing physics in the German magazines is gradually starting to change to English at this time. It was the first of three, and this first paper in July, the subsequent ones in, I think, September and November of 1913, expanded on the theory. But the fundamental idea in this paper was that according to the above considerations, where he was discussing problems with the structure of atoms that were very poorly understood at this time, we're led to assume that these configurations will correspond to states of the system, by which he means the electrons in orbit around the nucleus, in which there is no radiation of energy states, which consequently will be stationary. And so for the first time, the idea of having an electron, which is a particle, somehow orbiting, but somehow not orbiting at the same time, was made public. And this created a lot of controversy, as long as the system's not disturbed from outside. So he did his early studies in Denmark and then went to Cambridge to do a postdoctoral fellowship under J.J. Thomson. Thomson had already won the Nobel Prize by this time for the discovery of the electron. And Thomson had his own pet model for the atom, which nobody liked. The last thing he wanted was a brash, young Danish-speaking, broken English-speaking postdoc who kept trying to talk to him about the deficiencies of his model for the atom. But what Thomson discovered was that there was common behaviour of the subatomic particles that seem to be generated by hot filaments, by the light, the things that were generating the light coming from red hot metals, and the conduction of current through wires. And one of Thomson's famous experiments is this one right here. I have to be careful I don't blow my delicate silicon electronics with this, where he took a high voltage discharge in a tube of rarefied gas, and something is emerging from the cathode under the high voltage stimulus, streaming through the tube and impacting with the glass at the far end, and you can see the shadow of the Maltese cross that's inside the tube. And that's something originally called cathode rays, Thomson concluded was a new particle called the electron that manifested itself in all those different phenomena that I just described. And Niels Bohr had already done a PhD thesis on properties of metals using this newfangled idea of the electron. So he was well primed thinking about subatomic particles at this time. But he didn't get on with Thomson. Thomson was the head of department and far too busy to talk to junior staff, and I know the feeling all too well. He decided he would move on from Cambridge after a few months and went to Manchester instead. And at Manchester, thanks Steve, at Manchester, Ernest Rutherford was running an incredibly productive group on the discovery of the atomic nucleus and the start of nuclear physics. And this portrait here, which you probably, you can just see the signature in the corner, I've got the original here, this was presented to me by Betty Leiby, the daughter of Thomas Leiby, a former head of school. This portrait was actually given to Thomas Leiby in 1914 when Leiby was a professor of physics in New Zealand, and it's actually signed by the great man himself. So I regard this as a very precious link between today and the events of 100 years ago, and it's just terrific to have Rutherford's actual signature on his portrait here. But what Rutherford was doing was discovering the nucleus, and the way he was doing this was in a very ingenious way. He recognised that radium, when it decays, emits a subatomic particle, not an electron, but an alpha particle. And I've got a reenactment of that experiment here today. I just want to show you this. I have to put these gloves on because the radium source that I'm using here is emitting alpha particles travelling at about 10% of the speed of light, and although they'll stop, hopefully, in the epidermis of my skin, nevertheless, the general principle with radiation, if you can avoid it, you should, and so I'll put these gloves on just to be on the safe side. So what I've got set up here, yes, thanks Steve, if you could put that off. What I've got set up here is a very simple experiment. I've basically got a piece of radium. Let's face it, it is a real piece of radium in this box here. And facing the piece of radium, I've got a silicon surface barrier detector. And simply, there's a gap of a couple of centimetres between the radium and the detector, and the detector is very sensitive to light, so I have to put the lid on here to keep the light out. And every time an alpha particle emerges from the radioactive decay of the radium, it travels across the couple of centimetres of air, bouncing through the air molecules and eventually landing in the detector, and you can see the alpha particle signals as they collide with the silicon detector. And I can show their alpha particles with a very simple result of just moving the detector further away. And now the signal falls off much faster than you'd expect from the inverse square law, because the alpha particles are now almost completely blocked. In fact, I've moved them so far back they're out of range and they're not making it into the detector anymore, because the energy of the alpha particles is not enough to get through 8 centimetres of air. But if I move it back closer again, we now will see the signal reappear. And indeed, there they are. The peak is lower than it was a moment ago because it's now about 4 centimetres of air instead of 3 centimetres of air. And so they've lost quite a bit of energy in ploughing through the air. If I did that in a vacuum, they wouldn't lose so much energy. But what Rutherford did, he said, okay, these alpha particles can be used to probe the nucleus, or probe the atom, because it wasn't clear what the atom was, apart from this model that Thomson put forward that nobody liked. And this was basically the idea. You take an alpha particle, actually these ones aren't the radioactive ones, so I can take these off, and scatter them off the nucleus. And so you haven't got any control over how close the alpha particle goes to the nucleus, but if you do this experiment over and over again, you can gradually build up a picture of what's happening inside the atom. And this is how Rutherford discovered the nucleus. And so in the early 20th century, the way you did this was to put your radium inside this tube, so there's a little narrow opening where the alpha particles can come out. You put it inside a vacuum system so you don't have to worry about all the energy loss in the air, and as the alpha particles emerge, they're allowed to impinge on a very thin gold foil, a gold foil that's so incredibly thin it was expected the alpha particles would just pass through without stopping. But what Rutherford discovered was that every now and then an alpha particle would undergo an incredibly violent collision, like this, and basically recoil back out of the gold. And this was totally unexpected if the Thomson model of the atom was correct. There should be no way you could get a recoil, because this implied that there was something in the gold foil that was incredibly tiny and incredibly dense that was scattering the alpha particles. And indeed, that was Rutherford did some calculations on the basis of how many alpha particles scattered. You could see the alpha particles colliding with this scintillator here with a microscope. Each alpha particle makes a little flash of light, which you can see in a darkened room. And he was then able to reverse engineer the nucleus, reverse engineer the atom, and figure out that most of the mass of the atom was in this tiny nucleus. We do this in the basement of the building here from time to time when we want to measure what's going on in an unknown sample. And the basic idea is that we take a beam of ions and we scatter them off the nucleus here, and on the basis of the number of particles scattered through the angle, a particular angle, and the energy that they scatter with, we can tell what's going on inside the sample. You can download your own copy of this movie from our website if you want. And of course this was terrific stuff, totally unexpected. Nobody expected to find a nucleus inside an atom, and so this was worth a Nobel Prize. But at the beginning of the 20th century, the divisions of science and physics and chemistry were not yet well defined, and so indeed Rutherford, much to his surprise, got the Nobel Prize for chemistry, not for physics, for discovering the nucleus, even though chemistry doesn't say anything about the nucleus, only about the outer shell electrons in, if I may say, obsessive detail. But anyway, nevertheless, Nobel Prize for chemistry. But this Bohr knew about Rutherford's results and had his comments over and over again how much he enjoyed working with Rutherford in Manchester. And this became a very exciting and intense period of his life where he developed the idea of the quantum atom. And for a long time, other people had been trying to do the same, but they weren't bold enough. Everybody knows that the Earth goes around the Sun, well, since Galileo anyway, 406 years ago, where the Earth is held in orbit by the pull of gravity. And because the Earth has a substantial orbital speed of 30 kilometres a second, it doesn't fall into the Sun, it instead goes around in its orbit. And so it seemed like a simple step to take this idea and apply it to the atom, taking Rutherford's newly discovered nucleus and putting electrons in orbit around it, now held not by gravity, but by the electric force, the mutual attraction between a proton and an electron. And Bohr worked out this should be about 1/10 of a nanometer in diameter, this object. But there was a problem, because already by 1911 it was known that if an electron goes into circular motion, it's accelerated. And that, because its velocity vector is changing direction, and that acceleration should cause the electron to radiate energy away into space, which would allow it to spiral down until it collided and stuck onto the nucleus. And indeed, that's how the Australian synchrotron works. It's got electrons orbiting inside this big ring at very close to the speed of light, and the acceleration as the electrons pass through special magnets causes them to radiate very vigorously, very bright X-ray radiation. So Bohr had to solve this problem. And this is how he solved it. He said, okay, let's imagine there's something rather non-classical going on in here. So rather than thinking of a solar system, imagine the electron exists in this stationary state where it doesn't suffer the radiation problem. And you can visualise this as imagine getting something that's a wave and trying to put it around a nucleus. This wave has the wrong number of wiggles in it, and it isn't continuous, it doesn't meet up. So this wave would oscillate around all over the place, it wouldn't be a stationary state. Let's tweak it a little bit, tweak it a little bit, tweak it a little bit, until finally, bingo! We've now got a wave that fits perfectly around the atom. The wave joins up with where it started from, and this is a stationary state. And trying to imagine the electron existing as a stationary state is quite difficult. And this caused a lot of controversy when Bohr put this idea forward. Furthermore, Bohr said, well, what happens now if there's more than one stationary state? So basically, here's the situation. I can flip my nuclear model over, and we can reuse it for this. Basically, the idea here, you can imagine this is an electron, and it's now approaching the nucleus, but now the electron has a negative charge, the nucleus is positively charged, it's going to be attracted. And so, well, obviously that's a disaster. What we want to see is the electron somehow orbiting here, but in a stationary state. And here friction takes the role of the radiation that comes about from an accelerated charge, and so quickly spirals down to the nucleus and stops. That's no good, that's not a stable atom. So Bohr took this, he said, let's imagine these stationary states exist inside the atom, and imagine further that there's more than one of them at increasing diameters of the orbit, and let's then imagine that radiation, light, photons are emitted whenever an electron descends from a higher orbit down to a lower orbit between two stationary states. And let's imagine that that photon is emitted with a frequency, with an oscillation that's got nothing whatsoever to do with the oscillation of the electron. It's simply got to do with the difference in energy between the initial state and the final state. There is no mechanical oscillation going on here. This is not a transition that can be understood by the laws of mechanics and ordinary classical physics. This was a second rather radical idea. Now, in physics, it's fine to have radical ideas, but it's not fine to have radical ideas that don't work. So, what Bohr had to do with these radical ideas is find a physical system that he could apply them to. And of course, the hydrogen atom, the simplest possible element in the periodic table, a single proton with a single electron in orbit around it, was already known to produce a spectrum of light. Steve, can I get the, I just have to flick this.
Yeah.
Get the spectrum up. Not that way. Not that one. Oh, there we are. So what I've got here up here on the stage is a tube of hydrogen gas with a high voltage discharge running through it, and the light from the beautiful pinky blue light here is fed out through a prism and then into a camera. And we can see that this pinky blue light has got a number of different colours hidden inside it. There's a red component, there's a blue component, and what's happened to our other two? If your eyes are very good, you'll see another two that were there before the lecture started, but I've faded away a little bit. Let's see if I can make them appear.
Turn out the lights.
Yeah, maybe I need to take the lights down completely off. The young people, oh yeah, I can see it. There's one there, and there's another one, another very faint one over here. Now, the interesting thing about this is that it's these colours are surprisingly well spaced. They're not uniformly spaced, but they're spaced with the suggestion that they follow a mathematical progression. And that mathematical progression was already worked out before Bohr. But he was able to take his theory about the stationary states and the photons being emitted and say that this first red line comes about from an electron dropping from level 3 down to level 2. And the blue line here comes from level 4 dropping to level 2. And this purple line, which is very hard to see here, comes from level 5 dropping down to level 2. And he worked out what the colours of these lines should be and was absolutely spot on to a precision of 1 part in 10 to the 5. And this was breathtaking. And indeed, this diagram in his Nobel lecture, when he got the Nobel Prize for this in 1922, is now the prototypical Bohr atom, and even in the logo of the International Atomic Energy Agency, we still see the Bohr atom making its appearance 100 years later. Now, there's another issue of scale here which is important to keep in mind. This is a picture from the trip my wife and I made to Southern Europe in September last year. This is the Roman amphitheatre at Arles, and this is a very good model for the Bohr atom. But this is definitely not to scale. If we were using this, the Arles amphitheatre here, the arena rather, as a model for the Bohr atom, we'd have to get the nucleus in the right scale. And so if you imagine these people are looking at the nucleus here, and it's just a 12-point Times New Roman full stop on a piece of paper in the middle of the arena here, that would be the size of the nucleus that Rutherford had discovered a few years earlier. And here then is the first allowed orbit of the electron running around this level here. And you can see there are higher levels the electron could be excited to if it absorbed a photon, and if it dropped back down, it would re-emit the photon. So this is the correct scale for the atom as it became understood in Bohr's time in 1913. And in Bohr's paper, he attempted to go beyond hydrogen with not a great deal of success, because there are several things in his model that were missing. And we now know that as you scan up through the periodic table and add more and more electrons to atoms, the order in which they fill is fairly complicated. It's not so simple as you'd expect from just simple energy considerations. There's a whole lot of stuff to do with angular momentum, and it's really quite complex, but well understood and built on Bohr's first attempt. Now, as with any scientific theory, particularly one that was accurate, it created a lot of interest. And as far as we know, the first time Bohr's ideas were exposed to the scrutiny of the wider scientific community was right here in Melbourne. Just on a year after Bohr published this groundbreaking work, there was a meeting of the British Association for the Advancement of Science here in Melbourne. There had been precedents for this association meeting elsewhere in the Commonwealth. It had met once before in Canada. Most of the other years it had met within the UK somewhere. But in 1914 it met here in Melbourne. And in the physics department here in Melbourne, a briefing for the scientists was arranged by Sir Ernest Rutherford to tell us all about the Bohr atom. If anyone here today was present at that briefing, could they raise their hand? Some of you look like you might have been. No, that's fine. That's all right. Just for the record, kids, I wasn't there, all right? Before my time. This is what Flinders Street looked like in 1914. This is a map of Melbourne that was given to the delegates with places of interest marked in red. Everybody who was anybody in the British physics community was there, except Bohr, who had gone back to Copenhagen at this point. But the President opened the meeting with this address. It seems appropriate at this meeting in the city of Melbourne to mention one who passed away from his scientific labours somewhat previous to the last meeting. I allude to William Sutherland of this city, whose writings have thrown so much light on molecular physics and whose scientific perspicacity is only equalled by his modesty. And that's a very true statement of my great predecessor, William Sutherland, in this role as head of school. But there are a few other comments made at this meeting that I thought would be worth reading out. Rutherford had already said to Bohr, "Your ideas as to the mode or the origin of the spectrum of hydrogen, which we just saw here, are very ingenious and seem to work out well. But the mixture of Planck's ideas with the old quantum mechanics makes it very difficult to form a physical picture of the basis of it." Rutherford, the great classical physicist, is looking for a physical, mechanical model of the Bohr atom. No such model exists. "It appears to me one great difficulty in your hypothesis, which I no doubt you fully realise, namely, how does the electron decide, in the gas of hydrogen here, what frequency it's going to emit when it passes from one stationary state to the other? It seems to me that you would have to assume the electron knows beforehand where it is going to stop." Well, that's quantum mechanics for you. He also said, "The draft of your paper exceeds the attention span of an Englishman." So Bohr responded with a new version of his paper, which was even longer. James Jeans, the great British scientist and cosmologist and astrophysicist, said, "The only justification for the two postulates was the very weighty one of success." Okay, and furthermore, and I hope I'm not stealing Harry's thunder, who may cover this point next week, at the British Association meeting, it wasn't just restricted to physicists, chemists were invited along too. Do we have any chemists in the audience right now? Uh-oh. Well, I'm going to press on. The chemists, Professor Armstrong, who was the spokesperson for the chemists, because the Bohr theory was discussed at length in a joint physics and chemistry session. Professor Armstrong said, "Although chemists must admire as well as welcome the bold attempt physicists are making to unravel the structure of the elementary atom, they cannot yet with advantage discuss the conclusions arrived at by their colleagues. The arguments used are so novel and so daring, the contentions so original," I think that's not a compliment, "that at present they are not in a position to appreciate, still less to criticise them effectively. In fact, the chemist's office at the moment must be mainly to point out the conditions that a theory must satisfy to meet his requirements." There were only blokes as chemists in those days. Notwithstanding Marie Curie's Nobel Prize shortly before. The chemist has been long prepared to believe that the materials spoken of as the elements in the periodic table, may prove eventually to be compounds. Indeed, the relationships between them are so similar, and so on. But the views that are now advocated by physicists are entirely different from any conception that chemists have ever entertained and cannot easily be assimilated by them. Physicists, unfortunately, in the past have held aloof from chemists. they've paid too little attention to their methods and to their results in the movement now in progress, and it's therefore the initiatives of the physicists are to be welcomed, as it must have the effect of leading the two parties, the physicists and the chemists, in future to work together to a common end, hence the value of the present discussion. Prophetic words, but the collaboration is still a work in progress after 100 years. All right, so you can, from these quotes, you can get a feel for some of the contentious and exciting debates that took place on this campus 100 years ago. So I now want to fast forward to talk about some Bohr atoms that Niels Bohr would have been astounded to hear about, because he could have had no idea at any of these beyond the first one in 1913. But his theory of the stationary states, the mathematics, everything works perfectly well for all of these sorts of atoms. And they're very strange atoms indeed. First of all, there's the hydrogen atom, a single electron in orbit around a proton. Bohr's theory says that it takes 13.59 electron volts of energy to rip that electron away from the ground state. Here is an isotope of hydrogen, which was discovered a few years later, called deuterium, consisting of a proton and a neutron in the nucleus, again with a single electron in orbit around it. Now here we've got a positive charge, just a single proton, a negative charge. You might argue that this should have exactly the same physics as that, as the hydrogen atom, but it doesn't, because just as the electron orbits the proton, so does the proton orbit the electron. And you'll have to forgive me, I'm using quantum doublethink here. Nothing's orbiting, it's a stationary state. But quantum doublethink, which is a term I invented myself, says if you're going to understand this, you've got to ask, what would this do if it was a classical particle? Oh yeah, now we can understand what the quantum mechanics is telling us. Right? And so here is my very low budget demonstration of this principle. Here I have the proton, the electron, connected not by the electric force, but by a piece of aluminium. And what I'm going to do is turn this on. I can find the switch. Where's the switch, Steve? I keep breaking this every time I use it. And Steve has to keep, oh, here we go. Oh, there we go. So what I've got is the little red light here at the centre of mass. So where this thing more or less balances is where that red light is located. And if I now throw this across the lecture theatre, Harry, would you mind making sure this doesn't hit anyone? That's a big ask. Notice the trajectory of the red LED as it propagates through the lecture theatre, rotating vigorously. Oh, thank you, Harry. I think you'll have noticed that it executed a perfect parabola, as you'd expect from a throw from the Head of Physics at the University of Melbourne. And the two masses orbited around their common centre of mass. And indeed, that's what happens with all these atoms. I'll leave that on, because I've lost the switch again. And so therefore, the energies, because the proton plus the neutron weighs twice as much as the proton here, this means the binding energy, the energy of those stationary states, is very slightly different. You can see in the second decimal place here, 13.59 instead of 13.60. And this very slight difference meant that the colours of the lines seen in the spectrum from deuterium are very slightly different to those of hydrogen. And when these were detected in high-resolution spectroscopy, deuterium, the heavy isotope of hydrogen, was discovered, naturally occurring in the water of the Earth. And indeed, in the 1930s, the battery acid from Melbourne trams became naturally enriched in deuterium, as the acid always boiled and bubbled away as the trams were trundling around charging the batteries. The lighter water containing ordinary hydrogen evaporated in preference to the heavier water containing the deuterium, and so the physicists here in the 30s would collect the battery acid and take the deuterium out of it and use it for nuclear physics experiments. Also, Bohr could apply his theory to a helium nucleus with a single electron, that singly charged helium, very high binding energy. and also predict the colours that this ion would emit as the electron jumped up and down, and indeed these were discovered experimentally and they were in exact accord with Bohr's theory. But here's a really strange one. This is muonic hydrogen. Here, instead of an electron, there's a negatively charged subatomic particle called the muon. It's very short-lived, about 2.2 millionths of a second, so this type of hydrogen doesn't last very long. But the binding energy is enormous because the muon is very heavy and orbits very close to the proton. I'll come back to that in a minute. Here is also positronium. This is a very strange type of hydrogen, in inverted commas. It's not hydrogen at all. It's a positive electron, an anti-electron, orbiting the mutual centre of mass halfway between an ordinary electron. And this exists for a very short period of time in your brain if you are having a positron emission brain scan. The positrons from the radioactive decay of the isotopes they inject into you to make the image emerge from the radioactive decay from the carbon-11 or fluorine-18, and then they find an electron, they do this mutual orbit around their common centre of mass until they eventually collide with each other and decay. Muonium is a negative muon, that's an a positive muon, sorry, an anti-negative muon with an electron around it. And here even is an exciton. I'll come back to that in a moment. This is something that exists in a silicon crystal in electronics. And finally, the big one, the phosphorus donor in silicon, which I'm going to talk about at some length. Let me just go back to the muonic hydrogen for a second. This is ordinary hydrogen, proton and electron, and you put them together and the electron orbits overlap and hold the two protons together in a hydrogen molecule about 1/10 of a nanometer across. But if you replace the two electrons with two muons, because the muons are much heavier, they pull the two protons together much, much closer, and to be precise, 207 times closer. So these two protons are really close, they're almost touching in this strange sort of variation of the hydrogen molecule. Nothing much happens, the muons soon decay. But if instead you replace the two hydrogen atoms with two isotopes of hydrogen, the deuterium that I mentioned already, and a radioactive isotope, tritium, which is a proton with two neutrons. Deuterium and tritium love to get together and undergo nuclear fusion. And indeed, when you replace one of these electrons with a muon, the two isotopes of hydrogen are pulled so close together, the nuclei touch, they fuse together, a neutron is spat out, and now you've got a fusion byproduct, an alpha particle with the original muon in orbit around it where it soon decays. So this is cold fusion. This does work. You've just got to have a source of muons and you can produce fusion power with this method. The downside, which is why it has not yet been commercialised, even though this muonic hydrogen has been known for 50 years, is that the muon loves to stay attached to the alpha particle as a sort of heavy kind of helium ion, and it decays and is no longer available to create a second fusion event. And this is called the muon sticking problem. And so you've got to have an enormous source of muons to make this work, and it's very expensive to make muons. You've got to first make pions, which decay to muons. You've got to have a high energy particle accelerator. You might as well just burn coal. Now let me turn inward again to the silicon crystal and talk about excitons. So a silicon crystal has a whole lot of silicon atoms held together with electrons in very fancy Bohr orbits, well beyond what Bohr could have done in 1913, but the principles are all there. And in this crystal, you can replace one of the silicons with a boron and one of the silicons with a phosphorus. Now, boron has one electron too few to make the bonds necessary with the surrounding silicons, and the phosphorus has one electron too many. So this missing electron is like a hole, and at room temperature this can wander away through the lattice because an electron from a neighbouring bond can drop in and make it a double bond like everywhere else. And so now we've got the hole over here, the electron over here, and sure enough they orbit each other, even though the hole is a missing object rather than a present object. It has effectively a positive charge, and this is called an exciton. It's an electron-hole pair inside the silicon lattice. And this exists for a short period of time with all the energy levels predicted by the Bohr theory until eventually they annihilate, the electron drops into the hole and a photon is radiated away instead. And that photon carries information about the quantum state of any nearby phosphorus atom. More on that later. Here is what a phosphorus atom looks like, as best we can tell, inside a silicon crystal. All of your electronics in your laptops and your computers and your mobile phones contain phosphorus-doped silicon with a phosphorus atom substituting for the silicons. Here is an inner shell of tightly bound electrons, which don't do very much, and here is the fifth electron in loose orbit around the phosphorus atom, and this is with the crystal cooled right down. So instead of all the silicon atoms doing this, which is what they're doing at room temperature, the crystal lattice has been damped because it's very, very cold and the electron is at home orbiting its host phosphorus atom. As best we can tell, of course, the electron is in a stationary state, a Bohr orbit, around what is effectively a phosphorus ion. And Lloyd Hollenberg and his team have done a lot of work to calculate exactly what the electron looks like in this scenario. So if I get rid of the classical picture, this false colour image in the background is how that last electron is distributed around the crystal lattice. Lloyd Hollenberg and Cameron Wellard did this calculation using a supercomputer. You can see the nature of the wave function of the stationary state. It's dispersed in a sort of complicated donut-shaped orbit with peaks at the position of the neighbouring silicon atoms. We can use this, but we need some new physics before we put it to work. After Bohr, people added to the theory to make it better, beyond hydrogen. Developing the idea of the electron wave, you have to impose symmetry. The nucleus is heavy but not infinitely heavy, as I've described. Energy has to be conserved. The electron wave function, the description of where it is in this wave, has to have a single value at each point. There can't be two numbers for the electron at each point. And also, in some atoms, the electrons are orbiting so fast, quantum doublethink again, relativistic effects are important and the electrons are very heavy. And finally, the electrons and the nucleus both spin about their axis. So this is my poor man's model for a nucleus spinning with this arrow indicating the direction of the angular momentum. So my fingers curl in the direction of the spin, my thumb points in the direction of that arrow. And here in orbit around it is a spinning electron. There's a very classical picture here, of course. Nothing's orbiting, it's a stationary state. So it's actually a very complicated situation here, which we can harness to good effect. Applying all those things on the previous slide leads to these very colourful renderings of what the electron orbits look like. Here's the ground state. It's like a spherical shell of probability of finding the electron, and it turns out the angular momentum of that state is zero. So that's really hard to visualise. You've got an electron orbiting the nucleus, but with no angular momentum. Good, you've got an image of that? I certainly don't. And then these are higher levels where the electron contorts itself greatly in order to comply with all those rules on the previous slide. And here is an example of relativity at work. This is a wonderful app I have on my iPad. I highly recommend it. You can click on, this is a periodic table obviously, you can click on each of the elements and you get beautiful pictures of different manifestations of the element in art and technology. It's worth noting here that there's Rutherfordium down here, element number 104, and Bohrium, element number 107, the two stars of tonight's show. But you'll notice just about everything in this periodic table is metal, apart from a few non-metals over here. And one that stands out here is gold, which is different to all the other metals because it's yellow. And indeed, what happens in gold is the electrons are going so fast they disrupt the delicate ordering of the electrons that pack in around the gold nucleus. as a result of relativistic effects due to the relativistic mass increase. And that disrupts the energy levels ever so slightly, which means that gold metal absorbs blue light and therefore reflects everything else, and hence it appears yellow. So here we see a relativistic effect in the Bohr atom. Anytime you want to check that relativity works, oh yeah, gold, yeah, all right, it's all working. It's a wonderful application of relativity to quantum mechanics. But as I've mentioned, the atoms also are spinning. And this was discovered by looking at light coming from the sun. If you look at a particular colour of light coming from the surface of the sun near a sunspot where the magnetic fields are very strong, you see the line splits into three. And this is the interaction between the sun's magnetic field and the orbiting electrons in hydrogen gas. If I put a very strong magnet on this pink light here, and we had very high precision prisms in this, you would see these lines begin to split into sublines as a result of the magnetic interaction. And it turns out not only is there this effect due to the orbiting electron, this effect also occurs with the spinning electron. And remarkably, it was found that space itself is quantized. And the Stern-Gerlach experiment from nearly 100 years ago now, the guys who did this sent this postcard to Niels Bohr to announce their great discovery. They found that the electrons in a silver atom could have only two possible orientations, a spin up or a spin down, and nothing in between, because space itself is quantized. You can't have your spinning electron occupy any orientation in space it likes. That's the rules of quantum mechanics. So this then brings us to the quantum atom in technology. It's a remarkable fact that the transistors in your mobile phone are now so tiny that the smallest functional component is only 22 billionths of a nanometer in diameter. And this is only a factor of 10 times bigger than the size of the Bohr atom of the dopant elements, principally phosphorus, but sometimes antimony, arsenic or bismuth, that's in that transistor. So in other words, if you cooled these transistors down to liquid helium to stop the silicon crystal lattice doing this sort of stuff, and you cooled it down so that all the electrons occupied their orbits and hadn't been thermally excited, your devices, your mobile phone, would be sensitive to the quantum state of the electrons in their stationary state orbits around the dopant atoms in your transistors. Do not drop your phone into a vat of liquid helium. Who knows what might happen? So classical technology, as predicted here by the Intel Developer Forum in 2012, is already entering the quantum realm. And these classical devices, 1.4 billion transistors on this chip, could be used for doing experiments on quantum mechanics, the quantum mechanics of the Bohr atoms. So this then leads us to engineer a device where we deliberately exploit the quantum atom for storing and processing information. This is a device which has been built in collaboration with my colleagues in the ARC Centre of Excellence for Quantum Computation and Communication Technology. This device is only of the order of 100 nanometers in size, and to give you an idea of how small this is a polio virus, only 25 nanometers in diameter. A whole lot of complicated electronics here, and this device comes down to Melbourne, where we implant a single phosphorus atom into it using a tricky technique which we've developed for just this purpose. Here you can hear single phosphorus atoms landing in a block of silicon. Obviously, we turn it off when we had one, but there's 10 for you. 12, 15, 20. Okay, there's a whole lot. But you can turn it off after only one, and this is how we've been able to engineer a device with a single atom in it, a single phosphorus atom in a block of silicon. This is what the device looks like from inside the device. There's the phosphorus atom represented by this red nucleus here. An electron is put on it. There's a pulse of photons that happen to be in the radio frequency part of the spectrum, and there's a single electron transistor here which is used to read the device out. This is how it works. If there's a magnetic field, the electron spin, as I've already shown, can only have two allowed orientations in space, and you can flip between them by hitting it with a photon in the Bohr way. This is now a way of making a qubit. If you hit it with a second photon, you induce the decay back to the ground state and you get two photons out, according to the Bohr theory. So what happens if you turn the photons on and you leave them on? It means that the spin orientation of your electron is up and down simultaneously. And so if we call this a 0 and we call this a 1, these two different orientations, 0 and 1, this is now a quantum bit that we need to have in two states at the same time. And then when we read it out, that's just the spooky quantum mechanics right there. The electron spin is up and down at the same time. Okay, that's enough of that. When we read it out, we'll read out only the classical values of either down or up over time. And you'd expect, and the way you do this is with the single electron transistor that's nearby. You can adjust the energy levels such that you get this transition down to the ground state here, and you get a flow of current through the transistor, and you can tell what orientation the electron's in. And if it's already in the ground state, there's nowhere for it to go, and you don't get a flow of current. So if this was a classical system, every time you measured it, you get a 50% probability of being spin down and 50% probability of it being spin up, just at random. And Galileo Newton would be pleased. That's the classical result. But when we do the experiment, we don't see that. We see that the probability amplitude oscillates with time. This is the signature of the quantum system being in two states at the same time. Instead of it always being 50%, it oscillates between 0 and 1, but gradually it decays to the classical value of 50%. So this is a working qubit. And when my colleagues in Sydney, principally Andrea Morello, who was the architect of the device, and his student Jared Parr, who did the measurements, saw this working for the first time, they rang me up and said, "It's working." I said, "Great, don't touch anything. I'm coming." I went straight to the airport, flew to Sydney. I was in the lab 2 hours later, and I could see with my own eyes this happening. It was a wonderful, wonderful experience to watch a single quantum electron in a quantum superposition. But then things didn't look very good, because the electron pulse suddenly jumped to the other side of the oscilloscope screen, suggesting that the energy levels had somehow changed and we needed now a different colour of radiation to promote the transition. It looked very unstable. And I was panicking. But my sage colleague said, "Don't forget, the electron is orbiting a nucleus." And what we've just seen is the nucleus spin flip from the down position to the up position, and the magnetic force between the nucleus and the electron has changed the resonance frequency. So in other words, not only were we reading out the electron spin orientation, we were reading out the nuclear spin orientation at the same time. And so this led us now to doing the same experiment I just described with the nuclear spin. And because the nuclear spin sits down inside the atom, it's serene and isolated from the outside world, the oscillations go on for ages. And using the nuclear spin as a qubit, up and down, would be a very stable and long-lived quantum bit which you could do a lot with, an enormous amount. In fact, one of the best quantum bits of any system under consideration today. There was also a subtle little extra tweak. It turned out that the nuclear spin also resonated at two different frequencies, and that was due to the presence of a nearby silicon-29 atom. Most silicon is silicon-28, but there's about 4% of this annoying extra isotope which has a spin-half nucleus. The nucleus spin of that flips around all over the place and interferes with our quantum superposition. But we've got a new silicon crystal where all the silicon-29 has been removed, and the results, the news is really good because the oscillations go on forever, effectively. So finally, what are we going to do with this, or where would this go in the near term? Well, Australia in 2050, hopefully, will not be producing as much carbon dioxide as it is now. And there'll be a constellation of different sources of power running our country. Wind, tidal, residual coal and gas, solar and solar thermal, possibly nuclear, although that's controversial, and there'll also be electric cars, hopefully with big batteries providing backup power. And what we're going to need here is a smart control grid, a grid which is capable of switching enormous amounts of power around the country on short time scales. As the sun goes behind a cloud, as the wind strengthens and weakens, as people come home and plug their cars in to charge them up. And this grid control network has to be secure because you don't want people to hack it. So this leads to the quantum internet of the mid-21st century based on matter qubits in silicon. You can take your excitons, couple them to the nuclear spin, transmit the light down a fibre into a receiver, decode the quantum superposition and receive instructions. And this is completely secure because this is what you'll get if the flying qubits, the photons, pass down your optical fibre without being intercepted. But if someone intercepts the signal, instead of getting these oscillations, you'll just get 50-50 spin up, spin down, as encoded in the photon. And you'll know that someone has hacked your secure communication system and you don't trust the data anymore. And so I would say the quantum internet, using this sort of technology, will have to go hand in hand with the development of the smart grid of 2050, which we're going to need to meet the Garneau targets. So I just want to conclude by paying tribute to Alan Turing. He was a very advanced thinker. He actually drew up the blueprints for one of the first electronic computers using vacuum tubes in the late 40s, which was actually built. This is a prototype in the Science Museum in London, and just about all subsequent computers using classical principles owe a tribute to this pioneering work. And it was a tragedy that his life was cut short so early. But I just want to conclude with the words from Niels Bohr. He wrote to his wife from Manchester, I think it was, "My courage is ablaze so wildly as these crazy quantum ideas came out of his pen into the publications and eventually a year later were exposed to the public down here in Melbourne as he blazed a path to the quantum atom." Thank you very much for your attention. Very happy to answer a couple of quick questions. Gentleman down the front.
Yeah, appreciate that, Professor. Thank you so much for that. We need more international students. We need more PhD for future physics. We don't need money for another genocide for Melbourne University and MIT University. You talk about the future. I explain the future. We don't know future, we live now. What do you think future science, technology, and society look like what?
Okay, well that's a very big question, but I would give a short answer to a big question and say that I think quantum technologies are going to be very important in the future. We're just learning to understand the quantum atom, how to engineer quantum states into atoms, and I believe, as Professor Hollenberg also described last week, this will form the basis of a new way of looking at the world and a much more powerful way of computing. And computing drives our civilization, and so this is really central to what we do and how we live. Maybe I'll take another question. Gentleman in the blue shirt.
Okay, I've got a quick question. Yeah, with your diagram of the electron spin oscillation. Now, maybe I'm misunderstanding something, but when you measure the electron spin, wouldn't you destroy the superposition state?
Indeed you do, and indeed you do. So I should have mentioned, you never actually see the electron spin up and spin down. So it's only doing this when you're not looking. As soon as you look, spin up. spin down. And so it's only when you're not looking that it's in the superimposed state. As soon as you turn off the microwaves and then turn on your single electron transistor to measure it, you see either up or down, nothing in between.
So are those from many different experiments then?
Yes, many different experiments. So depending on how long after you turn off the microwaves you make the measurement. So it's oscillating in its quantum mechanical way because it's spin up and spin down at the same time. And then gradually that decays away until you just get 50-50, like a classical system. Yes, gentleman with the dragon on his t-shirt.
I've been reading about how both Google and the NSA have recently commissioned a 512-qubit quantum computer.
Yes.
That they've been experimenting with, and they programmed some incredible mathematical equation which they said a classical computer will take the age of the universe to have so many different variables to calculate. And they had this particular 512-qubit system calculated within a matter of minutes. But some people involved with it have made the interesting comments saying they don't even understand where the answers are coming from. It's almost as though it's just pulling answers out of the ether. They don't even understand how it fully works.
Okay, so I guess the question is, how does the quantum computer that Google purchased, and also Northrop Grumman also purchased a smaller version for 20-odd million apiece. What is that device? So that's a device that uses superconducting flux quanta instead of electron spin, based on niobium circuits. And it's not actually, as far as I can understand, a programmable quantum computer in the way that we're trying to build here. That seems to be like having an array of magnets suspended on strings interacting with each other, and you tweak one magnet and the magnetic force propagates through the array of spins and they settle down to a new configuration. It's called adiabatic quantum computing. So it's maybe a quantum analog computer, in the same way people used to wire up capacitors, resistors and inductors to solve partial differential equations. Not a general purpose machine, but you're emulating one set of phenomena with a different set. There's quite a bit of controversy in the literature as just how quantum these computers are. They're made by D-Wave systems. You could ring up and order one, have your gold American Express card ready. They're not cheap, but I have to, these guys have put their houses on the line to build these machines and sell them. It's a very brave, pioneering work. Welcome to the 21st century, I think we're seeing here. But it's not, as far as I can tell, a general purpose programmable machine. Yes, gentleman down here.
How far away are you from a
Okay, so in the words of Niels Bohr, predicting the future is very difficult, especially in advance. Actually, we're in a university laboratory, so we will not be making a quantum computer, but we believe that the technologies we've pioneered, and indeed the method for implanting single atoms into a block of silicon, has now been written into the international technology roadmap for semiconductors as a potential technology that the classical semiconductor industry may want to pick up. So it'll be left to someone with very deep pockets to build the fab to make these things. We still have to figure out a way of putting 1 million phosphorus atoms in a row deterministically into a block of silicon, because that's the degree of complexity that you'll need to do useful quantum calculations, and that is a problem that we're grappling with. We've done this great stuff, if I may say so myself, on single qubit systems, but that's like having one transistor and the market wants a Pentium chip. So there's a bit of a technology gap we have to address.
Your thing's 5 times bigger.
Big yours?
Your thing's about 5 times bigger.
That's right, but the memory is just one atomic nucleus. Okay, I think there was the gentleman with the hat was next. Yeah.
With enough initial outlay, could we have a feasible energy source from muon cold fusion? Or does it take more energy to actually get it to happen than it does produce?
Making muons is a really difficult problem as far as we know, and our friends at CERN who've been messing around discovering Higgs bosons and all that sort of stuff, haven't figured out how to make muons cheaply. And if anyone's going to do it, it'll be those guys, because the muons could be used for a lot of other things besides muon catalyzed fusion. It seems to be a very, very difficult problem. Muons are produced in cosmic ray showers. If you fly, you get direct personal experience with muons crashing down through the aircraft 10 kilometres above the Earth. No, producing them artificially, after 50 years of work, we don't see an easy way of doing that. So I wouldn't hold your breath on muon catalysed fusion as a sensible power reactor. To run our society, I should say, we need an enormous amount of power. To run Australia, we need something like 50 gigawatts, and that's an enormous amount of power. It's very difficult to imagine just how much power that is, and trying to imagine doing that with new technologies before the planet goes to 5 degrees above the mean, which I can't even imagine what that sort of planet would be like. I can't see it happening. We need to be able to back off our CO2 emissions by 2050, not by 100 or 200 years hence. So I'd be backing the low CO2 technologies that are available today, but you won't like it. Most people. Perhaps in view of the lateness of the hour, I'll just take one further question from the gentleman here.
If you had to discuss the theory of how does the electron determine the frequency when it drops down, and what the photon oscillates at, or what its frequency is, and you said it wasn't known then, is it known now, and is there a theory?
This is the way photons work. It's a rather dissatisfying answer, but that's it. There isn't, I can't give you a mechanical picture of things wobbling and sliding down rails. There is no mechanical picture here. This is a quantum phenomena, and you have to really stretch to imagine exactly what's happening. You can use a bit of quantum doublethink and imagine the electron actually drops from a high level to the lower level, but actually that's not what happens. The electron is in both levels at the same time. The photon kind of comes out of that using quantum principles.
The colour that you would see.
Yeah, the size of the drop determines the colour. Yeah, so these red ones are dropping over a relatively short distance, relatively low energy. The blue one here is dropping from much higher up in the hydrogen atom, and the electrons got into these higher levels by being bombarded with the stream of high voltage electrons passing through the rarefied gas. They're always lifting electrons out of the low energy states and putting them into the high energy states, and then they cascade back with this. And we'll hear a lot more about that from Harry's talk next Friday. We invite you to that. Okay, folks, so thank you again for coming. Please